Hi, this is Kevin Turner from Spanish River High School in Boca Raton, Florida. Welcome back to AP Daily for Introduction to Maps, Video 2. So what are we going to learn in this particular video? The first video, we spent a lot of time talking about the topic, the content. But what's content without skills? The skill that's been married to this particular unit a lot is data analysis. And it's the skill of basically taking what you see on the map and understanding the patterns that you see that are going to be quantifiable geospatial data. Again, what's geospatial data? It's data that's connected to a particular place on the Earth. So we learned in the last video that thematic maps can show us that quantitative data. Geographers will then look for spatial patterns or relationships in the data that's presented on the map. These patterns can be measuring distance, direction. They can be described as being either clustered or dispersed, or they can represent changes in elevation. Let's take a look at some ways that that can happen. So when we measure location, distance, direction, those can be done either absolutely or relatively speaking. When we say absolute, we're talking again about quantity. You see a lot of numbers here. The GPS coordinates of Boca Raton, Florida, the absolute distance from Nashville, Tennessee, where I was born, to Denver, Colorado. If you're heading due south and you're looking at your compass and you get a reading of 180 degrees, all of those things, location, distance, direction, absolute. On the other hand, relative is going to be a qualitative measurement. You have to know where something else is in order to be able to understand the location, the distance, and the direction. So my house is near the beach. Well, you wouldn't want to walk it. It's about 12 miles that way. All right. My school is a short drive away. Well, was there traffic? Was he going the speed limit? Did he hit every green light? I'm on the other side of the store from you if you're texting or calling a friend. Where are you? So again, all of these are relative to something else that you know the position of. So what will the geographers look for? Again, they're going to look at those patterns and processes. The pattern is what you see, right? It's the where question. The process is the explanation. It's the why there. And in this class, you're going to learn a lot about why and how things are happening. So when you see patterns and you have to start thinking about processes, I want you to think ESPN. I want you to think economic, social, cultural, political, environmental. You have to work with me a little bit on the end, okay? But when we see a pattern and we start to ask how or why that pattern exists, that's where we're going to use the ESPN. And we're going to describe the patterns that we see as being clustered, or they might say grouped, nucleated, clumped, concentrated. These words are all substantially equivalent to each other. Later in the course, you might even learn the word agglomeration. It always means clustered. Or we might see a pattern that's dispersed. It's distributed, it's scattered, it's spread out. Remember in video 1, we talked about different kinds of maps and showing different ways to show data, right? An area of density or concentration, that would be a great choropleth map. An area that's distributed or spread out, that would be a great place to use a dot map. So what other possibilities might there be? Sometimes there could be a uniform pattern. It's all evenly spaced out. There might not even be a discernible pattern. It might be randomized, right? Or we could show elevation. And again, I want you to think isoline there. That's the one that looks kind of like the thumbprint, where you get all those squiggly lines, and every time you cross a line, it means that you're changing elevation, right? The undulation of the terrain. Is it flat? Is it mountainous? Is it hilly? So let's look at some examples of these so that we can visualize, all right, what we mean. Here's a map showing the concentration of COVID cases in Seminole County, where I grew up. Right away, look at the title, the word concentration. It kind of clues you in. Look what we've got. We've got an isoline map. We're crossing lines to change data, but they've also colorized it. So it's a little bit of a choropleth effect as well. And remember, darker usually means more. Up in the top right-hand corner, you can see that the darker red colors there means more cases. And clearly, you can identify 3 places where there's concentrations of those infections. That's what we mean by clustered, right, or concentrated. If you look at this map, it's showing you rural health hospitals, critical access hospitals, right? The areas that are shaded gray are rural parts of the country. That's why there aren't really any dots anywhere else, because those are urban areas. We're talking about rural hospitals, right? That's the theme of this map. And you'll notice, especially if you zoom in right there in the center of the United States in Kansas, you can see that there's almost a perfect equidistant line of dots, right? This is not a concentration, right? It's a dispersal of those dots across that rural landscape. Each of those hospitals about the same distance from each of the other hospitals. So here's a map of Acadia National Park. We talked about elevation being shown on maps and seeing that pattern. Well, this is kind of famous in northeastern Maine, Cadillac Mountain. You can go up and see the sunrise early in the morning from the peak. Well, look at the map. It shows us that the lines are close together as we go up the ascent to the top of the mountain. And the farther away the lines are, we know that that terrain is going to be flatter. You'll notice on the right-hand side of the page there that there's a major road that kind of goes through that flat part. Well, that makes sense. You know, you're not necessarily going to build the road on the steepest portion of the terrain. You're going to build it in the flatter part, right? So again, we can show elevation using these maps. So let's practice. What kinds of questions might we see that's going to ask us to use some of these skills? This map is a choropleth map. We can clearly see the data as the shading gets darker, the elevation of the data, and it says percentage of women who are working in agriculture. Right? And the first question, it's going to give you a prompt. It's going to say women compose 1/3 to 1/2 of all agricultural laborers, yet empowerment and gender equality have been difficult to achieve. The first question asks you to identify a country where more than 75% of women are working in farming. Well, we can see lots of countries that we could name, right? We could use Madagascar. We could say Mozambique. We could say Chad or Niger. So then they want to say, okay, for each of the following 3 categories, and notice those categories are economic, cultural, political. Hey, remember ESPN? It's going to say to describe one obstacle from each of those categories that may prevent women working in farming from achieving empowerment. Now, in video 2, I'm not going to ask you to understand all of the processes, economic, cultural, and political, that might explain the answers to that question. But trust me, later in these AP Daily videos, you will be able to answer those kinds of questions. For now, I want you to see the pattern, and I want you to be able to understand that there will be processes that will explain that pattern. So what should we take away? Let me tell you, big data is everywhere. Every click, every post on social media, every like, companies are collecting data about you, about all of us. All right. They're using it to get a competitive edge. For you, why is this important? If you can identify patterns on maps and in geospatial data, and more importantly, if you can help analyze and understand the how and the why that data is what it is, you're going to be very in demand. You're going to be a very hireable person because geography is very important. And if you can think like a geographer, that's going to be good for you. Coming up in the next few videos on AP Daily, topics 1.2, 1.3, we're going to dive even deeper into geospatial data and talk about how powerful it can be in helping geographers make decisions. Until then, thanks for watching. Hi, this is Kevin Turner again from Spanish River High School in Boca Raton, Florida. And today we're going to wrap up topic 1.1, Introduction to Maps, video number 3. So what are we going to learn in this particular video? I saw a funny joke a long time ago, and it was Columbus, and he's sailing across the ocean. And remember, Columbus always told his crew that the earth was round, and the men are all angry, and they're saying, every time we see you using a flat map. Well, think about it. It's kind of funny. You know, if the earth is round, why do we use flat maps? Well, the only real way to accurately represent the earth is with a globe, but those things aren't exactly pocket size. They don't exactly fit in the glove box of your car. So we have to use what we call map projections. And this is when you take anything that's round, anything that's got a curvature, and you're going to display it on a flat surface. The easy way to remember this is if a map lies flat, it lies. So taking the spherical shape of the earth, displaying it on a flat surface is called projection. When you do this, the earth is going to get distorted in some way. It's almost like taking a peel off of an orange and trying to lay it flat on a surface. It's going to tear, it's going to rip, it's going to stretch. So we need to understand that there are kind of different ways to do these projections. If it's a conformal projection, they're preserving shape, but they're going to really have a problem distorting size. If it's an equal area projection, they're going to be able to distort the oceans enough to preserve the size of the land mass, but sometimes the shapes can get a little bit wonky. So let's search up map projections if you get a chance later. right? You'll find hundreds of map projections. I'm not trying to scare you. I just want you to realize that there's a lot of different ways that we can depict the curved Earth, the spherical Earth on a flat surface. We'll only look at a couple here. Some of the map projections that I selected for you are some of the famous ones. All right, for example, the Mercator projection. What will we notice? Lines of latitude and longitude are going to meet at right angles. It's great for navigation. It's going to get horribly distorted, particularly as you get into the polar latitudes, way in the north, way in the south. Antarctica is going to look enormous. Greenland's going to be too big. The Gall-Peters projection, kind of an antithesis of Mercator. Here we're going to see some real problems in terms of stretching, right? And you'll see this in a second. The Robinson projection is kind of a compromise projection between the two. And then we're going to talk a little bit about Good's projection. And this is going to be one that also kind of takes equal area and conformal and combines the two. And we'll see it a lot in textbooks. The old textbook I used to use at my school, all of the maps in there were Good's projection. So let's look at some of these examples. Again, remember, if a picture's worth 1,000 words, a map must be worth 1,000,000, right? So here's that famous Mercator projection. And almost immediately, one of the things that students realize, they look up there at Greenland, they say, wow, Greenland's enormous. It's bigger than South America. You know the real truth? It takes 11 Greenlands to fit inside South America. This map is horribly distorted. Antarctica on here would be so big, they had to cut it completely off of the base of the map there. You don't even get to see it at all. Remember, Antarctica is round, but when you take a cylindrical projection like this and flatten it out, right, that circle is going to become a line that goes all the way across the base of the map. The Gall-Peters projection. Remember, I said it's kind of the opposite of Mercator, because again, look at Greenland up there. It's almost like Greenland became curved because we're trying to preserve the center here of the Earth. And so Africa looks almost a little too stretched. Sometimes they say this is almost like laundry hanging. You know, it almost starts to get that distortion there in terms of shape. So let's look at the Robinson projection. Remember, we said it's a compromise. I always remember Robinson because it's flat at the top and the bottom and it's curved on the sides. It's just one of those things I tuck away. Kind of like Mercator is going to have a big Greenland, kind of like Gall-Peters is going to have a huge Africa in the middle. Just certain things I remember about the different projections. For this one, right? Again, being a compromise, we can see that size and shape are better, even in the polar areas. So this one you'll see is used a lot, for example, in an atlas. It's used a lot to show data across the different places of the Earth, or trying to show all of the Earth at one time, right? And that's also true of this one, the Good's interrupted homolysine. What they mean by interrupted, I always say it kind of looks like some rogue kindergartner with a pair of scissors came in and cut out all the water so that we could better show the size and the shape of the land masses, right? Because of the interruptions that take place in the Indian Ocean, in the Atlantic, and in the South Pacific. So let's practice again, like we always do, with some potential test questions or questions that have been asked before that'll help you with these particular topics and skills. So they're going to give you a visual stimulus here. You've got a certain kind of map, and it says the map above represents what kind of projection? Well, if you remember what we were talking about, lines of latitude and longitude meeting at right angles, enormous Antarctica, Greenland's way too big, almost immediately it should be screaming out at you, oh, this is Mercator's projection. But we can even look at some of the wrong answers. Diverging lines at the poles. Diverging means they're going apart from each other. These are all parallel, right? Robinson projection, distortions at the equator. No, the distortions here are really in the polar areas. So we can even start to look at why all of the wrong answers are wrong. But of course, it's pretty obvious that this is a Mercator projection. Admittedly, that's a pretty easy question. Let's take it up just a half of a notch here. Every map projection has some degree of distortion because is a big word in our class. It always signals that we're talking about how or why. We're asking for an explanation here, right? A says a curved surface cannot be represented on a flat surface without distortion. Well, we know that's true. Let's take a look at some of the other answers. Parallels and meridians. Those are lines of latitude and longitude. They never cross at right angles on a globe. Yes, they do. The grid system is two-dimensional. The real world is three-dimensional. Okay, that's true, but it doesn't answer the question that's being asked. Notice that sometimes those distractors will do that. Earth is not a perfect sphere. Okay, also true. The polar areas are a little bit flattened. The Earth is a little more wider around than it is top and bottom, but again, doesn't answer the question about distortion. And latitude lines are shorter than meridian lines, right? So again, this one should be fairly obvious. We talked about anything curved, anything rounded that you're going to try and make flat, it's going to have distortion, right? So again, that answer is going to be up here. So what should you be able to take away from what we've talked about in this video? All maps are selective of information. That's true of all of topic 1.1, Introduction to Maps. What are we showing, whether it's a thematic map or whether it's a map projection? We have to select what we want to show. So different projections, just like different thematic maps, they're going to have different uses. Again, Mercator's map is fantastic for navigation. A goods map might be really good to show thematic data all across the Earth because we've taken out the water so that we can make the land more accurately sized and shaped and be able to look at patterns and relationships amongst that data. So overall, you've learned a lot about maps in this unit, in this particular topic. So we're done with the introduction to maps. Now, my colleague, Ms. Neuroth, will come in for topic 1.2, where she's going to be talking to you about geographic data. I hope you tune in to watch. Thanks.